Serial correlation is one of the defining headaches in time series econometrics because it means the regression errors are still carrying information across time, and once the residuals move together, the usual OLS inference starts to become unreliable. Serial correlation means the error in one period is correlated with the error in another period. That can happen because shocks persist, because important lagged variables were omitted, or because the model is otherwise dynamically incomplete. In macroeconomic data, this is more the rule than the exception. The first thing to remember is that serial correlation does not automatically destroy the OLS coefficient estimate. Under suitable exogeneity conditions, OLS can still be unbiased and consistent, but the usual standard errors are no longer valid, and OLS is no longer efficient. So once again, the main consequences show up in uncertainty and efficiency. Lag-dependent variables make this especially important. If the true process needs more lags than we include, those missing lags get buried in the error term. Then, the residuals inherit persistence. So serial correlation is often not just a nuisance. It is evidence that the model may be missing dynamic structure it should have included. The simplest diagnostic is an AR1 style test. We take the residuals from the original regression, regress the current residual on the lagged residual, and test whether R show equals 0. If it does not, then there is evidence of first-order serial correlation. In richer settings, we also include the regressors in that auxiliary regression, so the test remains valid under weaker conditions. The Durbin-Watson statistic is the classic exact test under stronger assumptions. It is roughly 2 times 1 minus RHO hat. So values near 2 suggest little AR1 serial correlation, while values well below 2 suggest positive serial correlation. It is useful, but not perfect, because its critical values come with a gray zone where the result can be inconclusive. For more general settings, the Breusch-Godfrey test is often more practical. It allows testing for higher order serial correlation by regressing residuals on multiple lagged residuals and the original regressors. That makes it more flexible than the AR1 only approach and better suited for realistic models. What do we do once serial correlation is present? One option is to focus on inference and use procedures robust to serial correlation. Another option is to model the error process and transform the regression so the transformed errors satisfy the assumptions more closely. That is the logic behind GLS and feasible GLS. Under AR1 errors, 2 common FGLS approaches are Cochrane-Orcutt and Preece-Winston. Both estimate the serial correlation parameter, transform the model, and then run OLS on the transformed equation. Preece-Winston keeps the transform first observation, while Cochrane-Orcutt drops it. That often makes Preece-Winston more attractive in smaller samples. So the main lesson is that serial correlation is a sign the error process still has memory. OLS coefficients can survive it, but standard errors and efficiency usually do not. Testing matters, and the fix depends on what you know. If you mainly need valid inference, use robust methods. If you trust an explicit error process, model and transform it. Serial correlation teaches a deeper lesson too. In time series, residuals are never just leftovers. They often carry clues about the dynamic structure we failed to model. Next, we finish the sequence with autoregressions, forecasting, and non-stationarity.